Our first example that we're going to look at is the synthesis example. That was the one where we said it was like a marriage. It's always an element plus an element forming a compound. Elements are always neutral. They become more stable ionic compounds during the course of the reaction. So we take neutral element magnesium, will turn into the cation +2 form of magnesium, and then nitrogen, the neutral element, will turn into nitride and with a -3 charge. We have to balance out the charges overall to make Mg3N2, and then balance the overall reaction using our blue coefficients with 3, 1, 1. The combustion reaction you were asked to do, there was a couple of them. Organic combustion reactions, which is where you have a carbon-based thing being added to oxygen, always 100% of the time make carbon dioxide and water. So we just have to balance the reaction overall with a couple of 1s and a couple of 2s. Our inorganic combustion is just like a synthesis reaction. It's just like an oxygen synthesis. So we marry the elements together. Aluminum and oxygen, the elements are neutral, but unstable. They stabilize themselves by gaining and losing electrons to have the same number as a noble gas. So aluminum would lose 3, oxygen would gain 2 during the course of a reaction. We balance out the charges to make Al2O3, and then we'd have to balance the reaction overall with our coefficients 4, 3, and 2. In single displacement reactions, you have someone cutting in. There's a element trying to cut into a compound. So fluorine, the element, is trying to cut into aluminum and oxygen who are dancing, and you have to decide who does the fluorine want to dance with, the aluminum or the oxygen. Fluorine doesn't want to dance with oxygen. If you accidentally tried to put F and O together, you would realize that both of them make -1 charges. F makes -1, O makes -2. And so, because they're both negative charges, they would repel one another. So fluorine does not have his eye on the oxygen, he's got his eye on the positively charged aluminum. So when you put +3 aluminum with -1 fluoride, we'll get AlF3. It kicks out the oxygen to be by itself, but oxygen's a Hofbrinkel. So we can't just write O, but we'd have to write O2. Then we have to balance the reaction overall with our blue coefficients, 6, 2, 4, 3. Double displacement reactions are where we're going to swap partners. So the lead is going to go with the bromide, and the lithium is going to go with the nitride. There's multiple kinds of lead. There's the +2 kind and the +4 kind. We know we've got the +2 kind based on how many leads are needed to balance out the charge on the nitride side. So +2 lead with bromide -1, we get PbBr2. When our lithium +1 goes with nitride -3, we'd get Li3N. And then we'd have to balance the reaction overall using our pink coefficients, 1, 6, 3, and 2. For the decomposition reactions, we said those guys are like a divorce. So we have to split our compound down the center. So hydrogen goes one way, bromine goes the other, and both of those are Hofbrinkels. So we would write H2 and Br2, and then a big 2 coefficient in front of the HBr. On the last page, we were asked to do both classifying the reaction and predicting the products. Number 18, I know is some kind of decomposition because I see a compound and an arrow. So it has nothing to marry. It has nothing to swap with. The only thing it can do is fall apart. And we learned during our notes that when carbonates decompose, it's a divorce where the metal gets custody of one of the O's. So the Rb goes with the oxygen, one of the oxygens, and then we have carbon dioxide left behind. We'd have to balance out the charges between Rb and O, so we get Rb2O, And then it happens to be balanced overall, so our coefficients in blue are all 1s. Number 19 we know is a double displacement reaction because I see a compound being added to a compound. So our iron goes with our nitrate, silver goes with chloride. There's multiple kinds of iron. The way we know which kind of iron we have is by looking at the left-hand side. We can determine using the chloride that the iron on the left has a +3 charge, so that means the iron also has a +3 charge. Since nitrate's -1, we get FeNO3, 3. Our other product would be silver +1, combining with chloride -1. Then we'd have to balance our reaction overall, 1, 3, 1, 3. Number 20 we know is some kind of combustion reaction because I see oxygen as a reactant. Something's burning. In this case, it's cesium that's burning. So that's an inorganic combustion. It's basically just like a synthesis reaction, but just a special kind of synthesis with oxygen. So we're going to marry together cesium +1 with oxide -2, get CS2O, and then we'd have to balance with our coefficients overall, 4, 1, and 2. Number 21 we know is a decomposition because I only see a compound on the left-hand side of the arrow. Nothing to marry it to, nothing to swap with, so we just break it down the middle. Potassium goes one way, bromine goes the other, and when you're making elements, be on the lookout for those Hofbrinkels. Potassium, K, is not a PS Hofbrinkel, but bromine is, so we have to put Br2. And then to balance overall, we need those blue coefficients, 2, 2, 1. Number 22 we know is a combustion reaction because we have oxygen as a reactant. We know that it's organic combustion because we have a carbon-based compound being added to that oxygen. Those products are always carbon dioxide and water, and then you just have to balance the reaction overall. For our last few, number 23 we know is a decomposition because I only see one thing on the left-hand side of the arrow. When chlorates decompose, the divorce happens between the Cl and the O. So the Cl is going to go with the strontium and the oxygen goes off by himself. Strontium's +2, chloride's -1, so we make SrCl2. Our other product, oxygen by itself, is a Hofbrinkel, so we can't just write O, but O2. And then to balance overall, we need a big 3 as a coefficient in front of our oxygen. 24 we know is a synthesis because I see an element added to another element. Elements are neutral, but unstable, and so strontium and nitrogen would come together to make an ionic compound. Strontium forms +2 charges, nitride -3, so when we make our neutral compound, we get Sr3N2, and then we'd need some blue coefficients there, so just a 3 in front of the strontium. For the last one, we know it's a single displacement reaction because we see an element being added to a compound. Yes, it's Cl2, but it's just Cl. So there's our element, and HBr is our compound. That's the one that we said was like somebody cutting in at a dance. So you have to decide, who does the chlorine want to dance with, the H or the Br? Well, when chlorine turns into chloride, the ion, it has a -1 charge. So chloride would not be interested in reacting with bromide because they're both -1. They would repel. The chlorine would rather go with the hydrogen +1 and kick the bromine out to be by himself. Since bromine is one of our PS Hofbrinkels, we have to write Br2, and then we balance with some coefficients overall.